The law of conservation of energy does not say that the amount of energy doesn't change in a system. It specifically says the amount of energy total doesn't change in a closed system. Now, what about for an open system? Energy is still conserved, but that doesn't mean that the amount of energy is constant in the system. When we have a conserved quantity, basically all that means is that if we have some of that quantity leave, it has to go somewhere. It can't just disappear. It can leave the system, but then it's somewhere else. So energy is a conserved quantity. If it leaves a system, we call that system an open system. And then we have some work to do to figure out where that energy went, or if we have energy entering our system, we might have some work to do to figure out where that came from. Energy can be transferred between systems in a few different ways. The first way that we look at in AP Physics 1 is through work, by applying a force over some distance. Up until this point, we've dealt with closed systems, where there was no work done on the system by any external force. Now, that isn't the case. Up until this point, we've dealt with closed systems, and in a closed system, we can say not only is energy conserved, but the total amount of energy is constant. So if we add up the total energy at some initial moment in time, and we add up the total energy at some later moment in time, we'll get the same two values. That will no longer be the case with open systems. Instead, we have to allow for the possibility that energy is entering or leaving our system through work. And so the equation we'll deal with now is work is equal to the change in energy. Now the change in energy here, what we really mean is the change in total energy, though that's not how it's written on the green sheet. The change in total energy, which is exactly the same as the total energy that we end with, minus the total energy that we start with. Whenever we do a change in something, it means the final value minus the initial value. So we could rearrange this equation, move the add the sigma EO to the other side, and we get the total initial energy plus the work equals the total final energy. So this looks very much like our starting equation, just with this one extra term. Whatever energy we start with, we're going to add some amount of work to that, and that might be positive work or it might be negative work to figure out how much energy we're going to end with. Now, positive and negative work we've talked about. So negative work is done when our forces are opposing the motion or trying to stop the motion of our object or of our system here. Positive work then would be the opposite, when those forces are in the same direction as the motion of the objects. So we might have a positive or a negative term there, which means that our final energy might be larger or smaller than our initial energy. One place we'll see problems like that we'll have to use this in would be a situation where we have friction between systems. We don't have a real easy way at our disposal right now to track that energy that we lose due to friction. Some of that energy becomes sound, vibrations in the air. We hear when two things rub past each other. Some of that energy, most of that energy, becomes internal energy, which is the jiggling of atoms within the objects. And so we experience that as an increase in temperature. We don't have a great way at our disposal in Physics 1 to calculate that value. So once we lose energy from a system due to friction, we're going to kind of stop paying attention to it for right now anyway. But we can figure out how much energy we do lose by using a calculation of work done by friction. Now, we could have other external forces. This is just one example. So we'll deal with those as they come up. This is an example of an open system that we could solve using conservation of energy, taking into account work done on that system. In this case, we have a block that's moving across a surface that has friction. So, a normal surface, not one of those funny frictionless surfaces we think about in physics sometimes. Because of that, we're going to have some energy that's changed into a form we can't track very easily. So our approach is going to be figuring out the work done by friction rather than the amount of energy that turns into sound and heat. So for this problem, if we decide to do this as a conservation of energy problem, our first step will be identifying what type or types of energy are changing, are present and are changing over the course of that block's run down the ramp. Now I do want to note here, this is actually a problem that you could have solved before we even started our energy unit by using dynamics, the Newton's laws stuff. You could identify forces parallel to the ramp and perpendicular to the ramp. The ones that are parallel to the ramp would cause acceleration parallel to the ramp. You could determine acceleration and then use kinematics equations to solve for the velocity when it gets down to the very bottom of the ramp. So this isn't the only approach to solving this problem, and you'll find that more and more as we go through physics, that there are a lot of different things going on in a single situation, and sometimes analyzing different aspects will give us different ways to solve the problem, but still end up with the same answer. That's a good check to make sure that we're really on track with these things, is if we have multiple ways to solve a problem, making sure that they give us the same result. So in this one, we start out with our block up high on the ramp, and it's going to end down low on the ramp. And that suggests to me that gravitational potential energy between the block and the Earth is going to change over the course of this block's run. The energy for that system will change. If gravitational potential energy is going to be something I have to consider, then I'll want to start by identifying what I'll use as my reference level. I usually use the lowest point that our object would get to as the reference level for this one. So it's going to reach the bottom of the ramp. So let's just put our reference level down here at the bottom. We'll say when the block is at the very bottom of the ramp, we have a gravitational potential energy for the block Earth system of 0 there. So we start off with some non-zero gravitational potential energy. We end with 0 gravitational potential energy. Our block starts at rest, and we're asked about the speed when it gets to the bottom of the ramp. Even if we weren't, though, we would have some intuition here that the block is going to speed up as it goes down the ramp. It has to have some change in speed if it starts at rest and it ends at the bottom of the ramp. And so if the speed is changing, we have kinetic energy changing as well. So I'm going to have to consider both gravitational potential energy and kinetic energy in this problem. And then we've got friction in between those. Friction is not a part of our block Earth system, and so friction is an external force on that system. That external force will do work on our system, so we have to account for how much work is done by friction. So we rearranged an equation a moment ago to get total energy initial plus work equals total energy final. And I think that'll be the most useful form of this equation to use. You could certainly start, though, with just work equals delta E and get to this point from that. Now, our initial energy in this situation, we said was going to be gravitational potential energy between the Earth, or for the Earth and block system. So that'll be UG, and that's initial. And then we don't have any kinetic energy at that point. There's no springs in the diagram here, so no spring energy involved. So that's it for our initial energy. It's just that gravitational potential energy between the Earth and the block for that system. We also have some work that's going to take place here, and I'm just going to specify that that is work that's going to be done by friction. And that's going to be equal to our ending energy. And our ending energy here is going to be, well, no more gravitational potential energy because we'll be at the reference level at that point. So we're just going to have kinetic energy in our final moment here. At this point, we can substitute equations for each of these terms. Gravitational potential energy, we can solve for that as the mass of our object times the acceleration of gravity for this location times the difference in vertical positions between our 2 kilogram block there and the reference level. So that's going to end up being our 0.5 meters there. Plus our force of friction, that can be set equal to delta E, but that's how we got the equation we're starting with here. So we need a different equation to solve for the friction, the work done by friction. So that would be force times distance times cosine of the angle. Now here we're looking at the force from friction times the displacement, or the magnitude of the displacement, times the cosine of the angle between those two. Equals kinetic energy is 1/2 mv squared. Now, looking through the variables that I have in this equation, we start out with m, and I know m, g, so m is the 2 kilograms, g will be the 9.8 meters per second squared that we're used to. This y difference from the reference level to our block initially, that's going to be 0.5 meters, so we know that value. Frictional force, I have a number for. Distance, that's the distance traveled down the ramp. I actually don't have that value, so that's going to be how far it travels this way to get to the bottom of the ramp. So I am going to have to make a calculation there. Let's see, and let's see, I know the angle here, and I know this side of this triangle, so I can do some trig to solve for that. The angle between the frictional force and the displacement, our displacement is going to be this direction, and friction is going to act back up the ramp. So that'll be 180 degrees, so I know that one. Equals the 1/2 times the mass, we know is 2 kilograms again, times our speed squared. We don't know that value, but that is what we're looking for. So that's okay to have as an unknown. So the only thing we have to solve for before we can finish this problem is d, the distance traveled. And so I'll do that using some trig. I have this angle 37 degrees, and that 0.5 meters, that'd be on the opposite side of this, this triangle. I'm imagining a second triangle that kind of occupies this space. So we're not quite using up the whole ramp here. So the distance that I travel is going to be the hypotenuse of that blue triangle. And then the 0.5 meters, that'd be the side that's opposite of that 37-degree angle. So to figure that value out then, I'll use the trig function that has the opposite side and the hypotenuse, that's sine. So sine of 37 degrees is equal to 0.5 meters, the opposite side, divided by the hypotenuse, which is going to be our d value. And so then I'll multiply both sides by d, divide both sides by sine of 37 degrees. So d is 0.5 meters divided by sine of 37 degrees. And that gives me d. 37 degrees is one of those values that's on the equation sheet, the list of known trig values. And so I can just look up a value for that, and this one, sine of 37 degrees, is 3/5. Now with the decimal in there and the fraction, that's not going to be real convenient to work with, so I need to simplify this a little bit before I do that. Be careful on this one. I see this mistake pretty frequently. Oh, 0.5 divided by 3/5, that'd just be 0.3, except it's not here. Divided by 3/5 is the same as times 5/3, times the reciprocal. So it's 0.5 times 5 divided by 3, so it'd be like 2.5 divided by 3. So that doesn't give us a nice easy fraction to work with. We can make it, 2.5 divided by 3 is the same as 5/6, but still it's not one that's going to have a lot of cancellations on there. So this is one where I might be inclined to do just a decimal approximation. You could certainly do that. Well, we'll go ahead and use the 5/6 that we get here. So it's 2.5 divided by 3, 5/6 of a meter. And then we'll just wait till the very end to get the decimal approximation with sig figs on this. All right, so at this point we can start plugging in values and solve for this. So our mass first off was 2 kilograms. G is 9.8 meters per second squared. The delta y was our 0.5 meters, plus our frictional force, which was 8 newtons, times d, which was 5/6 of a meter. And then friction is going to point up the ramp. Our displacement is going to be down the ramp, so our angle we said was 180 degrees. Equals 1/2 times 2 kilograms times v squared. All right, so let's simplify this and rearrange to solve for our value v. On the left side there, 2 kilograms times 0.5 gives me 1, and then times 9.8 just gives me 9.8. And the units there are kilograms times meters, and then there's another meters in there, so that's times meters squared divided by seconds squared. Now that's the same as joules. I'm actually going to leave it for the purpose of unit cancellation later. Kilogram meters squared per second squared. All right, plus our 8 newtons times the 5/6 meters times cosine of 180 degrees. Cosine of 180 is just -1. And so the 8 times the 5/6 gets us 6 2/3, and that'll be a negative. And at this point, I'm just going to make this 6.667. And then the units on that are newtons times meters. Remember, newtons are the same as kilograms times meters per second squared. So if I multiply that by meters, I again get kilograms meters squared per second squared, the same units as my first term there, which is good. And then we have on the right side 1/2 times 2 kilograms, so that's 1 kilogram times v squared. All right, on the left side, I'm going to combine those two terms, and so when I do that subtraction, I get 3.133. That's in kilograms times meters squared per second squared, and that's equal to 1 kilogram times v squared. All right, and then I'll divide both sides by 1 kilogram. The number doesn't change, but my units do. So I've got kilograms divided by kilograms. That'll just cancel out. Meters squared per second squared, and that's equal to v squared. And then I'll square root both sides. And I'm going to end up with an answer of 1.77. And the units, we have meters squared per second squared, but we square rooted that, so that'll be meters per second. And that's it. Now, as a point of comparison, if we didn't have friction in there, then the amount of energy that we started with would be the same as the amount of energy that we end with. So this is not part of the problem. This is just maybe a check that I would do to make sure this makes sense. If we took friction out, we would expect that that thing would move faster by the time it gets down to the bottom of the ramp. So if we took friction out, then we wouldn't have that friction term in our equation. So we'd have 9.8 kilogram meters squared per second squared equals 1/2 times 2 kilograms times v squared. And so I multiply the 1/2 and the 2, that gives us just 1 kilogram, and divide both sides, so I get 9.8 meters squared per second squared equals v squared. And then when I square root 9.8, I end up with 3.13 meters per second. Meters per second equals v. So I square rooted those. There we go. So the red v there, that's what we would have if we had no friction on this surface. And then the black is our actual answer to this with friction, and it's slower than the without friction case. So that's a good sign there. Sometimes it's a little tricky when we have to add in the work done there. People get confused on which side does that go in and what's the sign on that. So it's definitely worthwhile to think through this way. What if we didn't have that work in place? We would expect that it would go faster if we didn't have that work from friction. And so we can do a quick check there to make sure that our answer is reasonable that way. That's the most common problem I see on these ones, is just a wrong sign for the work or having it on the wrong side of the equation. And this check will catch that. So if we find that, oh, friction is making it go faster in my calculations, then we can go back and reevaluate what the sign on that work was or which side of the equation it went on. So that's it. We do have considerations for both work and energy combined into these open system problems. Doesn't have to be from friction. Any external force can do work on the system. So be aware of that and watch for that in problems that are coming up. Thank you very much, folks. If you learned something from this, please do subscribe and feel free to ask questions or share your thoughts in the comments section. Thanks again.